Good morning, my dear students. Today I would like to introducing the numerical methods. This is the last module of this course for the numerical methods. Before introducing the numerical methods, first of all, you have to introduce the introduction to the ordinary differential equations. The numerical methods, and in this module, we will learn numerical methods for solving the ordinary differential equations. So, in this lecture, I will introduce the ordinary differential equations to you. What we mean by the solution of ordinary differential equations, what type of ordinary differential equation we have, what is the condition for existence and uniqueness of the solution of a ordinary differential equation. And finally, we will talk about why we need numerical solution for ordinary differential equations. An ordinary differential equation is of the form f of x, y, y prime, y double prime, so on, which is equal to 0, which is equal to 0. So the ordinary differential equation, first of all, you have to introducing the order and degree. So what is the order of the ordinary differential equations? The highest order derivative occurring in the given relation is called the ordinary differential equation, and the highest order derivative exponent is called the degree of the differential equation, and it make it free from the fractionals and radicals and transcendentals. This type of equation is called the ordinary differential equations. Furthermore, we can classify the ordinary differential equations into two classes. One is linear and another one is the nonlinear ordinary differential equation. First of all, we have to discuss the linear differential equation. In linear differential equation, y and its derivatives are of degree 1 and there is no product of dependent variables and their derivatives. For example, x square into d square y by dx square plus dy by dx plus y is equal to e to the power of x. Here the dependent variable and their derivatives should not multiplying together. So then it is called the linear differential equation. Next one is the non-linear differential equation. The differential equation which is not a linear is called the non-linear differential equation. For example, non-linear differential equation means, so here the non-linear differential equation is the dependent variable and the derivative should be multiplying together. Then such type of differential equation is called the non-linear differential equation. For example, y square into d square y by dx square plus x into dy by dx plus y cube is equal to u to the power of x. U to the power of x. Some physical applications are there in ordinary differential equations. Like consider a simple pendulum having mass m, which is a hanging from a string of length L. Also, it is a fixed at a pivot point. When a pendulum is displaced to an initial angle theta and released, it will swing back and forth periodically. So F tangentially is equal to minus mg into sine theta, and tangential acceleration A tangential is equal to r alpha, where r is the distance of point from center of body and g is the acceleration due to the gravity and alpha is the angular acceleration given as alpha is equal to d square theta by dt square. Another application is there, that is growth and decay of the ordinary differential equation, exponentially growth and decay. A population of people, animals, or bacteria consists of individuals. The aggregate behavior can be effectively modulated by a dynamical system that involves the continuously varying variables. Varying variables. Varying variables. Exponentially growth and decay. In a simply way, the growth rate is assumed to be the independent of the population size. So the equation 2 becomes the linear differential equation. The solution which is given by n of t is equal to n naught into e to the power of alpha t, where n naught is equal to n of 0 is the initial population size. Hence, if rho is greater than 0, the population increases exponentially, and if rho is less than 0, the population at an exponential rate. Exponential rate. Let the nth order ordinary differential equation d power n y by dx power n is equal to f of x comma y prime y double prime so on y to the power of n minus 1. The general solution of the above differential equation will contain n arbitrary constants. So n conditions of y and its derivatives at one or more points must be prescribed to determine the constant inequality. The condition may be prescribed in two ways, initial value problem and boundary value problem. Initial value problems. In initial value problem, all the conditions are prescribed at a single point, that is value of y, y prime, y double prime, so on, y to the power of n minus 1 are prescribed at some point, say x is equal to a. In this case, solution is required in the domain x is greater than a, which means solution domain is open. For example, the first order initial value problem dy by dt is equal to minus 2 ty, and initial boundary initial condition is y of 0 is equal to 1, that is t is greater than or equal to 0. Second order initial value problem is, for example, second order initial value problem is d square y by dt square plus 5 into dy by dt plus 4 into y is equal to 8t square, comma y of 0 is equal to 1, y dash of 0 is equal to minus 7, comma t is greater than or equal to 0. So let us take next boundary value problems. So on the other hand, in the boundary value problem, the conditions are prescribed at two or more points, usually at two, says x is equal to a and x is equal to b, where b is always greater than a. So in this case, solution is required in the domain x belongs to a comma b, which is bounded. So this is if I take, this is first order differential equation d square y by dx square plus y is equal to 0, and here the domain is closed interval from 0 to 5. Then y of 0 is equal to 1 and y of 5 is equal to 1. Now we will take about the existence and uniqueness of the solution of a given ordinary differential equations in theoretical sense, means when the solution exists and if it is exist, whether it is unique or not, and if it is exist or unique, in which interval it is, means what is the interval of the existence or uniqueness, of the solutions. The existence theorem. So consider the first order initial value problem y prime is equal to f of x comma y and y of x naught is equal to y naught. Suppose that f of x comma y is a continuous function in some region, that is r is equal to set of x comma y such that modulus of x minus x naught is less than a, modulus of y minus y naught which is less than b, for all a comma b is greater than or equal to 0. Since f is a continuous in a closed and bounded domain, it is necessarily bounded in R. That is, there exists k is greater than 0 such that modulus of f of x comma y which is less than or equal to k for all x comma y is belongs to R. Then the initial value problem 3 has at least one solution y is equal to y of x defined in the interval modulus of x minus x naught is less than or equal to alpha, where alpha is equal to minimum of a comma b by k, a comma b by k. Next, uniqueness theorem. Suppose that f and dou f by dou y are the continuous function in a region R. Hence, both the function f and dou f by dou y are bounded in that region. That is, modulus of f of x comma y which is less than or equal to k, and modulus of dou f by dou y is less than or equal to L into for all x comma y belongs to R. Then the initial value problem has at most one solution y is equal to y of x defined in the interval modulus of x minus x naught is less than or equal to alpha, where alpha is equal to minimum of a comma b by k. On combining with existence theorem, The initial value problem has a unique solution y is equal to y of x defined in the interval modulus of x minus x naught which is less than or equal to alpha. Next, Lipschitz condition. However, we can replace the condition that is dou f by dou y is continuous and bounded in the given rectangular domain by a weaker condition. We can replace this condition by the Lipschitz continuity. The condition defined above can be replaced by a weak condition called the Lipschitz conditions. Thus, installed continuity of dou f by dou y, we have modulus of f of x comma y1 minus f of x comma y2 which is less than or equal to L into modulus of y1 minus y2 for all x comma y is belongs to R. If dou f by dou y exists and it is bounded, then it must be satisfies the Lipschitz condition. However, a function f of x comma y may be Lipschitz continuous, but dou f by dou y may not be exist. For example, f of x is equal to x square into modulus of y. Modulus of x is less than or equal to 1. Modulus of y is less than or equal to 1. Satisfies the Lipschitz continuity in y, but dou f by dou y does not exist at x comma y. X comma y. For example, to consider a initial value problem, y dash is equal to 4 plus y square with the initial condition y of 0 is equal to 1. Consider the rectangular domain R is equal to R is equal to x comma y such that modulus of x is less than or equal to 110 and modulus of y comma y minus 1 is less than or equal to 2. Since f and dou f by dou y is equal to 2y are continuous, so there exists a unique solution in the neighborhood 0 comma 1. Also, modulus of f is less than or equal to 3 in R. Therefore, alpha is equal to minimum of 110 2 by 13. This is equal to 2 by 13. So hence, by existence and uniqueness theorem, a unique solution is generated in interval. Generated in interval. Now in the I told you of the differential equations.